Alright, so here we are with the Chapter 5, Section 4 notes, and we're talking about multiple angle identities. So, on your formula sheet, you're going to see these new formulas. They're called double angle identities, and so again, it's just when we're using our proofs, what can you replace sine of 2u with? The whole idea is that anytime that you see a 2 inside of the sine or the cosine or tangent, it's going to be very hard to manipulate. And so in that case, you want to change it back to where it just has a variable and not a number and a variable inside of the function. And so that's what's happening here. We're taking away this double angle inside of a cosine or a tangent. So, interesting thing about cosine, of course, is that each of these can be found through your algebra process in order to get to them. So it doesn't actually matter which one you pick, because they can all be formatted from each other. So it's fine, but the idea is that, you know, if you pick one over the other, you may have more steps to do. So it doesn't necessarily change your answer depending on which cosine you take. For each of these, it just may take more steps to get there. Versus the sine and the tangent specifically equal each of these, at least more simply. So those are our double angle identities. They're new on our formula sheet, so something that you'll want to take a look at. And so again, taking a look at our formula sheets, so far we've done reciprocal identities, quotient identities, we've got Pythagorean identities, more Pythagorean identities because I altered them, cofunction identities, sum and difference identities, we just did those in our last one, and now we're on to double angle identities, so each of these is listed there. Alright, so we're going to prove this identity, and of course you can see hopefully that there is a cosine of 2a here, so a double angle. And so as we look at the formulas that were given to us, again we can just pick any of them. Hopefully taking a look at what you're trying to get later, you are trying to get a tangent squared at some point, and so it might be anyway, there's not a cosine and a sine in there, so picking one of them over the other doesn't really matter. So I'm going to pick this one here in the middle and try to solve it that way. So if we take a look at altering, let's see, the left side, I'm going to rewrite cosine of 2a via that double angle identity as 2 cosine squared a minus 1. Yeah, so you can see that now we have a 1 that's being added and a 1 that's being subtracted, and so we can probably go ahead and take those away. So let's see, this guy here and this one here. So now we have 2 cosine squared of a, and of course 2, if we want to separate this, could be 2 over 1, and cosine squared a could also be over 1. And so if we do that, we can actually change it. Ultimately, because I know that I want to somehow get to tangent squared, and I also want to get to 1 plus tangent squared, and so hopefully looking at our formulas, the 1 plus tangent squared hopefully reminds you of this guy right here. And so I'm looking at a cosine right now, and I'm trying to get a secant. So looking at how we can get a secant from a cosine is by rewriting this cosine as a secant. But cosine is on the top, and normally if it's 1 over cosine, that could be your secant. And so now I'm actually going to flip the roles. If cosine is on top, then that actually means 1 over secant. So over here, I'm going to rewrite cosine squared of a as 1 over secant squared of a. Because again, 1 over the secant is actually equal to the cosine in the numerator. And now, because of 1 over secant existing, I can then use my trig identity to rewrite secant squared a as tangent, 1 plus tangent squared. So I now have 1 over 1 plus tangent squared of a, and then we also have the 2 as well. So, finishing this up, of course, we can multiply that 2 across, and so we have 2 over 1 plus tangent squared of a. Alright, so our next one here, we're going to prove this identity. Hopefully you can see that it's a triple identity instead of a double angle. So basically what we're going to do is our previous idea of the fact that we can add angles together. And so in this case we're going to actually change this to sine of 2x, because we know that one, plus 1x. And so now we have an addition of sines that we can use. Our previous part of the formula sheet here, where we added sine angles together. So we're going to use sine cosine plus cosine sine. So we're going to do sine of 2x, cosine of 1x, plus cosine of 2x, sine of x. So we've rewritten this with our angle addition within an angle of sine. And now we're going to fill in our sine. So sine of 2x, we're going to use one of our formulas from this lesson, and cosine of 2x, we're going to use another one. So sine of 2x, I'm going to change to the only one that it has, so 2 sine of x, cosine of x, and then of course the same cosine of x that was already there. And then to that we're going to add cosine of 2x, which is going to be replaced with 2 cosine squared of x minus 1. And then of course the sine of x from the previous. Alright, so just a side note on why I picked 2 cosine squared of x as my cosine of 2x is because the other option has a sine squared in it, or a sine squared, and of course none of that is in what we're trying to get in the end, which is just a cosine squared, and so I ended up taking the one that used cosine squared in order to rewrite. So, let's see. In our next line, we're going to combine the 2 cosines, so 2 sine of x, cosine squared of x, just to kind of put everything together. And then we're going to distribute this sine in, so we're going to add that to 2 cosine squared of x sine of x minus sine of x. And then hopefully you can see that from there we have the beginning piece here, which is 2 sine squared cosine, 2 sine of x cosine squared of x, right here. And then we actually have this piece, which actually is 2 sine of x cosine squared of x, because multiplication is commutative. And so we have 2 of these, and another 2 of them, and so together we'll have 4 of them. And then of course this last piece that didn't combine with anything yet. Then taking a look at what we need for our answer, we're almost there. The only thing that is not happening is that we need this sine out front. So to take that sine out front, we're dividing it out of each piece. And so sine of x can get undistributed, and then we'll be left with a 4 cosine squared of x right here, and then minus 1, which is what we needed to get in the beginning. Alright, so the next one here we want to solve, so when we get our answer we don't have to say that it's a certain number and then plus 2k pi revolutions. We're just going to do it on 1 unit circle here. So again, solving is different than in this case proving, so we don't need to not move one of the sides or anything like that, and so in this case we can do things to both sides in order to simplify. So first of all, I see a double angle, and so I'm going to go ahead and rewrite that as its equality of 2 sine of x cosine of x. Then I see that there is a sine in both sides, so I'm going to go ahead and divide both sides by sine. And so the sines will cancel, and we'll be left with 2 cosine of x equals -1. Then to both sides, we're going to divide that 2 out. And so we're going to try to solve when is cosine -1/2. So if we look at our unit circle, when is the x value -1/2? That's here at 120 degrees and here at 240 degrees. So again, 0 to 2 pi means 0 to 360 degrees. And so in that case, we're going to say that x is going to equal 120 degrees or 240 degrees. All right. Then we have something called power-reducing identities. And power-reducing identities allows us to get rid of anything that's squared other than in a trigonometric identity. So basically what's going to happen is you're going to have proofs that have squares in them, and then they're trying to equal something that has no squares in them. And so in that case, you might be able to change it to something that has a double angle in it. And then, of course, from the double angle, you can go to our previous rules. So these are our power-reducing identities. And so, again, anytime that you see this, it's probably, or use this, it's probably because you're trying to get a result, like in this one here, that has a lot of power, but exponents, but then no exponents in the result. All right. So taking a look at what we have here in our example, again, this one is a proof, and so we're not going to do things to one side, and then the other, we're going to just rewrite one side so that it equals it versus doing operations to both sides. So taking a look at this and what we've just been doing, we have cosine to the fourth minus sine to the fourth. And so what we could do is rewrite these, because we do know that cosine to the fourth actually comes from cosine squared times another cosine squared. And then we also have sine squared and then sine squared, which could have been sine to the fourth. And so what we can do with that then is go ahead and rewrite our cosines and our sines as our previous identities here, the power-reducing identities. And so cosine squared is going to be rewritten as 1 plus cosine of 2 theta over 2 times another 1 plus cosine of 2 theta over 2. And then we could also have sine squared theta, which is going to equal 1 minus cosine of 2 theta. And then another, over 2. And then another 1 minus cosine of 2 theta over 2. And so again, we've written these pieces. So, as we look at this, we're going to go ahead and expand. When you do fractions, right, top times top and bottom times bottom, so they're both going to be over 4 here. Right, but these numerators are going to be a little different, and you're going to either do FOIL or you can do maybe the box to get the result here. And so I'm going to do a very condensed box for the left side here, so 1 and cosine of 2 theta, and then another 1 and a cosine of 2 theta. And so we've got cosine of 2 theta here when they multiply, another cosine of 2 theta, and then a cosine squared of 2 theta. So this numerator now becomes 1 plus 2 cosines of 2 theta plus cosine squared of 2 theta. And then our next one is kind of the same, only now it's 1 minus cosine of 2 theta. And so we'll have a 1, a negative cosine 2 theta, another negative cosine 2 theta, and then a positive cosine squared 2 theta. So our new numerator is going to be 1 minus 2 cosines of 2 theta plus cosine squared of 2 theta. This negative sign does distribute to each of these. And so as we look at simplifying, everything is technically over 4. Doesn't really change much. And then all of our pieces can come together. So I'll rewrite it here. So we'll have 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. But then minus 1 plus 2 cosine of 2 theta plus, minus cosine squared of 2 theta. So let's see. A positive cosine squared of 2 theta and a negative cosine are going to cancel. A 1 and a negative 1 are going to cancel. And so on top, we really just have 4 cosines of 2 theta over 4. And then, of course, the 4's can cancel. And so we're just left with cosine of 2 theta, which is what we wanted to begin with. Now, are there other ways of doing that? Of course. You could have done difference of squares, whatever it was. But, of course, there's a little bit of algebra to solve that. Alright, so the next problem here, they want you to rewrite cosine to the 4th in terms of trig functions with no power greater than 1. And, of course, that was the whole point of the double angle identity. The first one, of course, the first way that I could write this is kind of just going back to understanding powers anyway, which of course is that cosine to the 4th is actually just cosine times itself 4 times. But of course we could also use the double angle identities, and so that's going to mean that cosine to the 4th is actually cosine squared of x times cosine squared of x, and then due to the formula, cosine squared of x can actually be rewritten here as 1 plus cosine of 2 of that variable over 2. So 1 plus cosine of 2x over 2 times 1 plus cosine of 2x over 2. And of course you can simplify that, etc., but that's the idea. Alright, so then we have half angle identities. So instead of double angle identities, now there's a half involved inside of the sine or cosine or tangent. And so the idea is that it's a half of u instead of 2 of u, or the variable. And so now we have all of these options. So anytime that you are trying to get a half of one of the standard angles that are inside of the unit circle, you can use sine of u over 2 equaling this idea here. Cosine is going to equal this one, and tangent is these guys here. And of course it's plus or minus because potentially this was squared, and so you don't necessarily know if it was starting out as a negative that was squared, because that's positive, or started out as a positive squared, because that's still positive. So there is a set of 2 answers, just like in a quadratic equation. There could be a plus or a minus for your intercepts. So first one here is actually using this half angle identity with a value. Okay, so instead of putting it into an algebraic equation or a proof, we're talking about an actual value within it. So what we're going to do is find a value on the unit circle that makes 112, oh I missed one, that makes 15 in this case of sine. And so on your unit circle, 15 is not there, and so we could instead use half of 30. And so half of 30, meaning our u in this case is going to be 30 degrees, means that sine of 15 is actually going to have a u of 30, so it's going to equal the plus or minus of 1 minus cosine of 30 over 2. And of course we could get a digit for that and try to solve it. So the first thing that I would do is at least figure out that cosine, or note that cosine of 30 is square root of 3 over 2. And then from there you can kind of do a lot to figure out what common denominator could be, things like that. But it doesn't really help much. So I'm just going to do the next piece, but you could stop here. The idea is that you could have a plus or minus 2 over 2 minus square root of 3 over 2. That's because you're trying to find a common denominator. And then from there you could combine and get 2 minus the square root of 3 over 2. And then that's over 2 over 1. And so in that case you could multiply by the reciprocal, which means that you'd actually get plus or minus the square root of 2 minus the square root of 3 over 2 times 1 over 2, meaning a 4 in the denominator. So ultimately all of that work changes it from what we had up here with a little fraction in it to 2 minus square root of 3 over 4. So not huge in its difference, but there it is. Alright. So then if we move on to the next one, again 112.5 is not on the unit circle, but if we double 112.5, you're going to end up with 225. And so 225 is on the unit circle. And so we're actually going to end up saying that u is 225 degrees, and therefore we can plug it into the equation, meaning that we get plus or minus the square root of 1 plus cosine of 225 over 2. And so just like the previous one, I'm just going to at least plug in that cosine of 225, meaning the x value at 225 is negative square root of 2 over 2. And so I'm going to put negative square root of 2 over 2, and then of course still over 2. And then we can stop there. Of course there's a decimal equivalent, but that's not necessarily equal. So, alright, then the next one is tangent of pi over 8, and so we're saying how can I rewrite this pi over 8 in order to get it into a unit circle piece. To help us out, pi over 8, as much as we love that, we're going to make it into a degree. And so pi over 8 times 180 over pi means that we're actually looking at 180 divided by 8. Alright, and so 180 divided by 8, the pi's are going to cancel, leaves us with 22.5. And so 22.5 doubled is actually 45, and so we're looking at 45 degrees for the u value. So u is 45, and so we can pick any of these, and I don't necessarily want the square root one, so I'll just pick this guy over here. And so our answer is going to be 1 minus cosine of 45 over sine of 45. And on the unit circle, cosine and sine of 45 degrees is square root of 2 over 2. And so we're going to have 1 minus the square root of 2 over 2, and then the square root of 2 over 2. Alright. And that is the end of that. And so you'll be using each of these. There's kind of a few identities here. And so there are going to be a few less proofs in this one and more application, kind of like these problems where we just do it with a value. So that is our long multiple angle identities idea. Power reducing, half angle, and then double angle.